Hi, so today I'm going to talk about energy at the nanoscale. So why surface is important, we talked in previous lectures. And today we are going to talk about the surface energies and tension. So everything we talk has a surface. Right? So the first 2 to 3 atomic or molecular layers, we call it as the surface. Now, all these reactions we talk about between materials, they start at the surface. And surface atoms are different from the bulk material, the atoms or molecules inside the bulk material, because these surface atoms, they have fewer nearest neighbors compared to the bulk. The bulk compared to the atoms inside the bulk material. So inside the bulk material, the atoms, they are surrounded by the nearest neighbors, but in the surface atoms, they have nearest neighbors towards the inner side of the bulk material, but not on the top, right? So they have fewer nearest neighbors. And because of that, surface atoms are different, their energetics, therefore also different. So that's why we are going to talk about the surface energy and surface tension. So surface energy and surface tension used interchangeably. This is almost the same, but surface energy we mostly refer to solids, and surface tension we mostly refer to liquids. So why the surface is different? As we talked earlier, since surface atoms are undercoordinated, as I told you in previous slide, they have fewer nearest neighbors. The surface in general is unstable relative to the bulk, because the bulk material is surrounded, but here it's not like that. It is more exposed, therefore it's unstable. So there will be excess free energy stored in the surface. And it will take energy if you're going to create a new surface, like if you try to break up a material and make smaller ones. So you're increasing the surface, that means you're creating, or that it takes energy to create new surfaces. On the other side, if you're combining surfaces to make one, like say you have one water droplets combining to make one big drop, then energy will be released. So surface energy is always positive, and it is a driving force. So there's two terms, surface tension and surface energy. So surface tension, although it's often used, surface tension we mostly use with liquids. So if we talk about in terms of the units or the SI units, that is Newton per meter. Or another famous one is dyne per centimeter. Dyne comes with the CGS system, centimeter, gram, second unit system. So one dyne is equivalent to 10 to the power minus 5 that of Newton. Or surface energy, we talk about surface energy, especially when we're talking about a solid. And surface energy is presented in terms of joule per meter or erg per centimeter square. So on the right-hand side, I have given the associated equations that we usually use. So gamma here is intrinsic property of that material. So ES here is the surface free energy. AS is the surface area of that particular liquid or the solid. So if you want to find out the surface free energy, then you can take it to the other side, and then you can have the equation in terms of surface area and the factor gamma. So now let's assume for the time being that there is a material specific proportionality, and we call it this gamma, or in some cases we refer it as sigma. And it has a unit of joule per meter square, or that is equivalent to Newton per meter or erg per centimeter square. This gamma is an intensive property, and it measures the level of free energy available on that surface. So usually this gamma value is given if you're going to do a calculation. The specific gamma values are given for that specific material. And total surface energy, ES, is an extensive property, and it is measured in joules or ergs, and also depends on the total surface area. So this surface, this is the common phenomena, the surface of water, if you're going to talk about, which is abundantly available. So here's an example. Here's a floater floating or, balancing on the water. The water, we know, if we try to step on water, what will happen? We will go down, we will sink. But here, it is floating on it. And if you just, carefully look at it, where these insects' arms are resting, you can see it is more like an elastic membrane. It's dipped a little bit. It's deformed, but it's more or less like an elastic membrane. It's like, weighing on an elastic membrane. So the same thing, the water molecules in the interior are attracted to each other. They are attracted by gravity, they are repelled and compressed, but everything is done equally. So there's no net force acting on water molecules inside the interior water molecules. So there's no net force. And liquid, it's not like crystal, but the molecules are relatively organized because the molecule, if we take its H2O, so we have oxygen and 2 hydrogen atoms bonded. And then what happens if it has another water molecule near? There's O, which is slightly negative, and H slightly positive. So this O from oxygen atom from one water molecule is attracted to hydrogen atom in another water molecule. So they are kind of like, interacted. So even though it's not a crystal, these water molecules are orderly organized inside. That's why we have net force 0, because this water molecules is surrounded by other molecules. When it is inside, all the forces acting on it is balanced out, so no net force. But at this surface, what happens? It is covered by interior water molecules, but not from the top and above. It doesn't have the water molecules to have that sort of attractions or repulsions. So they are undercoordinated. So what happens? The pull towards the inside, the inward pull, and the lateral one, because it has nearest neighbors on the side as well as in the bottom side. So the inward pull and the lateral pull is more strong. This inward force is balanced by water's resistance to compress. You know that water is, it is compressible, but up to a limit. So that is compensated because of that. Then what happens? The surface molecules are, it has a tension and it is packed to form an elastic membrane. So this is a schematic representation of what's really happening. So we have the water droplet, we have water molecules, some are arranged on the surface and the others are inside. So if you take an interior molecule, what happens? No net force, it is pulled in all directions, it's balanced out, no net force, but on the surface, it has lateral pull as well as inward pull. So it has this tension creating on it, and this inward push is balanced by the resistance of water to compress. Therefore, what happens? the surface, the atoms on the surface will be densely packed, and that will more look like an elastic skin. So that's why you kind of like when you're when you're looking at that image of that floater resting on the water surface, it is more like it is resting on some sort of an elastic skin. So that's why this tension is coming into play on water. And that will again, I mean, if there's a water droplet, that's why it tries to make it into a, in a spherical manner. Or let's say the water is now leaking now from the tap, and when the water drop is, escaped from the this faucet, it will become a sphere. Why? That is because it has the lowest energy. The sphere has the smallest surface area of all shapes, and that will again lead to the least surface area. So that's why it comes into shape of a sphere. So to get a better idea about the concept I talked about, we'll do a small exercise that is broken up to 3 scenarios. This in scenario A, you are given 3 cubes, right? And you know on one surface, it has it has a gamma factor. So you will have to calculate, I mean, one surface area has surface free energy of gamma. So you will have to calculate the total surface area and then multiply it by the gamma value in order to get the surface free energy for that particular cube. So you have 3 such cubes. So you will have to multiply it by 3. So we have 3 cubes, and on each cube we have 6 surfaces, and on each surface it has a gamma value of gamma free energy. So in total, I mean, if we take the cubes separately, in total it will have 18 gamma of surface energy. What will happen if you try to agglomerate them into one rectangle? So what you do, you take these 3 cubes, put it into one, and make a one single cube. So here, when you're like, let's say you glued it or somehow you molded it, then we are going to lose 1, 2, 3, 4. We are going to lose 4 sides because of that molding. So we will see 4 surfaces lost during melding, and we will have to again calculate the surface final surface energy. Now we have in total 18 when we have it as separate cubes, and then by molding we lost 4, so we are losing 4 gamma of that surface energy. So it will result 14 gamma as the surface energy of the resulting this rectangular block. Then in the scenario B, you're taking this rectangular block, 3 of them, try to mold them together to come up with the, this block shown in the scenario B. So in scenario B, we are going to lose 1, 2, 3, 4. We are going to lose 4 3 gamma surfaces. Now here, this one side is equivalent to gamma, 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 3 gamma. So by melding, what happens? We're going to lose 1 3 gamma surface, another 3 gamma surface, here another 3 gamma surface, and another 3 gamma surface on this block. So we are going to lose in total 3 gamma surfaces, and for 3 blocks there are 4 sides, 1, 2, 3, 4, 2 surfaces from the middle one and 1 from the end blocks. So we are going to lose 12 gamma just because of we are molding these the surfaces. Right? So We know that one block has 14 gamma. Now we are molding three of such blocks. So we have 3 times 14 gamma. 14 gamma is one block. And then we will have to reduce by molding. We are losing 4 surfaces and one surface has 3 gamma. So when you do the math, you will be getting 30 gamma as the final total surface energy for the scenario B. Then what we do, we take such such blocks shown in scenario B, 3 of them molding together to come up with the block shown in the scenario C. Right, so if you take this one block here, it has a 30 gamma, right? No, it has a total surface energy of 30 gamma, but one will have 9 gamma surfaces. You can do the math and you will see this one will have 1, 2, 3. This will have 9 gamma surface, and then we are losing 1 from the end blocks and 2 surfaces from the middle block. Altogether, we are losing 4 surfaces again, and one surface will have 9 gamma. So we are going to lose 4 times 9 gamma when we are melding these these blocks together to make one. And we know in one block it has 30 gamma. So in such we have 3 blocks. So in total we will have 3 times 30 gamma, and we are losing 4 sides, 4 surfaces with each 9 gamma. So that will yield 54 gamma for the big block. So you can see when we keep on melding things to get a big picture, we are losing energy. So this is just a small exercise. You're given, you are asked to calculate the change in the surface free energy when 4 drops of mercury with diameter 250 nanometer, and you are given the gamma value for the particular mercury, and then these 4 drops coalesce to form one large drop with diameter capital D. So if we assume the isotherm conditions, then you can calculate the surface energy for the 4 drops. You can take 1 drop, you can calculate the surface area for that drop. You know the diameter, you know the gamma. Then if you know the surface area, you just have to multiply it by the particular gamma, and then you can come up with the surface energy for that particular drop. And then for such drop means you just have to multiply it by 4, right? So that's what is given here. And for the drop, for the large drop, so we had droplets here, we have one large drop here. You know the diameter of the big drop, that's capital D. So you know this gamma here. So you can, come up with an equation in terms of capital D for the total energy of this large drop. Right. So let's keep it aside, and then we can find out a relationship between the simple D and capital D. So in terms of volume, because these 4 droplets comes together to form the big one. So in terms of volume, if we add up the 4 volumes of these 4 droplets, that should be equal to the volume of the large drop. So by equating the volumes, we can come up with a relationship for the big drops diameter in terms of simple D, that is capital D equals simple D times 4 to the cube root. Then we can we are asked to find the change in the surface energy just by fusing these 4 droplets, or coalesce these 4 drops into one big drop. So to find it out, to find the delta ES, what we have to do, we just have to, we have to get the difference between these 2 energies. So obviously the area is bigger here, so we have bigger energy for the bigger one, and we will have to subtract the surface energy of the 4 droplets from the big drop's surface energy. And we know that capital D in terms of simple D, so we can replace capital D in terms of simple D here, and then finally, instead of simple D, we can use this 250 nanometer, and then you can see 1.44 times 10 to the power minus 10 millijoules is the difference when we try to fuse these small 4 drops into one big drop. So you can see there's a minus sign. Think of it, why there is a minus sign. So if you want to create more surfaces, you will have to do work on it, you will have to supply energy. And on the other hand, if you take smaller ones, if you try to fuse it, and then you try to make a bigger surface, then that will have the excess energy will be released. So the second example is what amount of excess energy is required to aspirate a droplet of water, and diameter is given as 300 micrometer. And what you will have to do, you will have to aspirate it into nano drops of 300 nanometer diameter nano drops. So you have a big one, 300 micrometer in diameter. You aspirate it to 300 nanometer diameter nano drops. So what will happen? You will have to calculate the amount of excess energy, or this extra energy that you will have to give to that water drop in order to aspirate them into nano drops. Simple. First, you have to calculate the surface energy of the droplets. You know the diameter. You are given the gamma factor for that water. So first you do the calculation for the droplets, which is 2.83 times 10 to the power minus 13 meter square. And you can calculate the surface energy for the large drop. Since you know it is 300 micrometer in diameter, you can calculate it. That is 2.83 times 10 to the power minus 7 meter square. And then you can calculate the volumes of these droplets. Then you're asked to, you are given the big water drops diameter. You know the diameter of the small droplet or nano drops, but then you can calculate how many nano drops you can create from that one big droplet of water, which is 300 micrometer in diameter. So to do that, you calculate the volumes of the droplets, and then you calculate the volume of the drop, and then you just divide the volume of the drop with the volume of the droplets, and then you will see you can come up with 10 to the power 9 droplets. If you aspirate, that will create 10 to the power 9 droplets with 300 nanometer diameter. So if you know the area of one single droplet with 300 nanometer, then by aspirating the drop, you're creating 10 to the power 9 droplets. Then you can calculate the total surface area of droplets aspirated from that 300 micrometer diameter big drop. So what you have to do, you take the number of droplets, multiply it by one single droplet's surface area, and there you go. You have 2.83 times 10 to the power minus 4 meter square total surface area for the aspirated droplets. Then you are after finding the excess energy that you need to provide in order to aspirate a big drop into smaller droplets. So to do that, you can calculate the change in the surface area. So you know the big drop has 2.83 times 10 to the power minus 4 meter square. And now, so all the drops have 10 to the power 2.83 times 10 to the power minus 4. And the big drop had 2.83 times 10 to the power minus 7. So here you can obviously see all the surface area of the droplets is increased. So you can find out the change in the surface area by, subtracting them and resulting a value of 2.82 times 10 to the power minus 4. So you have to do a work in order to aspirate the single drop into, that much of nano droplets. So to calculate that work that to be done, you know this gamma value for the water, and then you know the change in the surface area. So you just have to multiply. So you will have to give 0.02 millijoules in order to aspirate that one single drop into nano drops. So if you are interested, you can calculate the specific surface area of the two states. So you can calculate the specific surface area of the drop. So if you know the drop surface area, then you just have to divide it by the volume and the density. And just to convert it, you can use this conversion. So you can come up with the specific surface area as 0.02 meter square per gram. And for the droplet, you can divide it by the volume of the droplet, the density of the water, and then that will be 20.1 meter square per gram. So if you can just compare the specific surface area of the drop with the droplet, now the specific surface area of a droplet has increased 20 times, not 20 times, right? It has increased 1,000 times, 1,000-fold increase in the total surface area for the droplet. Right. So that will be for the today's lecture. So please do some more exercises. I'll be uploading a tutorial based on this surface energy and surface tension calculation. In the next lecture, I'll be talking more about energy in the nanoscale. So thank you very much. Even though tomorrow is a holiday, I'm going to upload the lectures so that we are not going to miss. We can go smoothly and finish it quickly as possible so that we can have some discussion classes. Thank you very much and see you all tomorrow.